In the previous lecture, while inferring stability from the Nyquist plots, we had explicitly said that the contour in the S-plane, that this should not pass through any singular point. So essentially it means that my contour should not pass through the pole. So for example, if I have a pole here, my contour should not go through the poles. This is okay, but there might be cases where there might be. So what did our contour look like? The contour looked like the entire right half plane, entire RHP of the form. So I did this. I'll use a different color. So this entire thing, right, of infinite radius. But there might be situations where I cannot avoid passing through the singular points. For example, if I have a pole here or a pole at the origin, I will have to pass through a singular point. So we will now discuss of how to avoid this situation. So welcome to this lecture number 3 of module 7 of the week on control engineering. So we'll now look at special cases of what we just talked about. When I say I have the open loop poles on the j omega axis. So somewhere maybe I have a pole here or a pole here. Okay, so when the open loop transfer function has poles on the j omega axis, the Nyquist plot must be, or the Nyquist contour must be modified to avoid passing through these singularities. It's largely necessary because the Nyquist criterion is based on the argument principle, which requires that a closed contour does not pass through the singularities. And if the closed contour passes through a pole of G times H, the mapping becomes undefined because I hit a singular point. So to handle such open loop poles on the j omega axis, so we are not worried about any other pole, we are only worried about what happens when I have poles of the open loop on the imaginary axis. In that case, we modify the Nyquist contour by just passing around the singularities using small semicircles of radius epsilon as epsilon tends to 0. So what I essentially look at is, so suppose there is a pole here. I just, okay, do a different color. Suppose there is a pole here. So I just go around this thing. So and I'll have epsilon e power j theta. So where epsilon goes to 0 and theta goes from minus pi by 2 or minus 90 degrees to plus pi by 2. Okay, so let's see what this actually means. So we'll just do a few quick examples and see what this means. So the first example we will look at is suppose here 1 over s ts plus 1. So g of s was 1 over s ts plus 1. Okay, we'll see if we had done something like this before. So go back, I just look at this plots here. 1 over s ts minus 1. Okay, let me see if I had the polar plot of that. Okay, as omega goes to 0 and goes to, oh, okay, so this was here, right? 1 over s ts plus 1. Okay, so what I here have is, so I can just by symmetry draw the plot that for, so this was omega equal to 0, this was omega equal to infinity, and so at this point was omega equal to infinity. Here we can say omega is minus infinity, it goes away and goes really far away and then comes back here. So what really happens at omega equal to 0? Okay, so I go back, I just write down a few things. So I have GS is TS plus 1S. So I write the sinusoidal transfer function. J omega is G of J omega is 1 over J omega T plus 1. So which means I have a pole at the origin here, and I draw a little small contour around this. The contour is such that this is epsilon e power j theta as epsilon becomes very small and theta goes from minus pi by 2 to plus pi by 2. Okay, so I just substitute for this in place of j omega. So I have g of j omega, or so this now translates. So I'm looking at limit epsilon going to 0 k over e power so epsilon e power j theta. Again, I'll have epsilon e power j theta plus 1. So this reduces to limit epsilon going to 0 k epsilon e power j theta, or also limit epsilon going to 0 k by epsilon e power minus j theta. So as epsilon goes to 0, this limit goes, or the magnitude goes to infinity. Okay, this is just around the singular point at j omega. And theta, so when theta goes from minus pi by 2 to plus pi by 2, e power minus j theta, this goes from pi by 2 to minus pi by 2. Okay, so and the rest all follows the same process. Uh, so we go back here and check what the Nyquist now looks like. Okay, so this will again go to infinity. Earlier this length was k, now this becomes k times t. Okay, and then what happens at omega is so I'm looking at a circle of infinite radius. Okay, so this is what the limit of epsilon going to 0 k over epsilon e power j theta uh, t epsilon e power j theta plus 1. Okay, so this curves we did in the previous lectures. So what really happens is now so just this, right? It just ends something like this. Okay, this is fine. We got the plot now. What about stability? Z was equal to P minus N. Okay, so open loop system is stable, P equal to 0. For stability, Z must be equal to 0. So this is just at the origin here. My minus 1 plus J0 is somewhere here. So the point plot does not encircle the minus 1 plus J0 point. So the system is stable for all positive values of the gain K. Okay, we do one more example where I have now two poles at the origin. So same situation. I have instead of so now I have K over S square Ts plus 1. In the sinusoidal transfer function, I can write this as j omega square j omega t plus 1. Now I look at what really happens around that little ball of radius e power j theta as limit epsilon goes to 0. Okay, so k limit of epsilon going to 0, k over uh, epsilon square e power 2j theta, which is a square, and this will be pretty so you'll have t epsilon e power j theta plus 1. So this will still be epsilon, so limit epsilon going to 0, k over epsilons e power minus 2 j theta. So as theta goes from negative of pi by 2 to plus pi by 2, e power minus j to theta goes from pi to a negative of pi. Okay, now this is around what happens around this singular point, around uh, epsilon equal to around this really point, around the singular point and the pole at the origin. Everything else we can compute as the earlier techniques. Okay, so I just have the plot like this. So this will go this way and so on. Okay, look at open loop. There are no poles on the right hand side. So Z here equal to, okay, this should be two encirclements, right? Because I'm just, okay, this should be 2 and 2. So Z has two encirclements, okay, or two encirclements in the clockwise, or minus 2 in the counter clockwise direction. So the closed loop system is unstable. So we had an open loop system which was okay. Let's also try to understand this from the root locus of why there are two poles on the right half plane. So so I have here two poles here, one pole here. So if I just draw the root locus, so this line will be on the root locus. Here, this and this. So this will be the direction. For any k gain k greater than 0, there will be two poles of the closed loop system on the right half plane. And that is what shows up here via the encirclements. And therefore, the closed loop system is now unstable. Okay, and then we can do several other examples around there, but the idea remains the same. Okay, so I look at three transfer functions here. The first one is k over s plus 1, s plus 2, and we'll see what happens. Well, maybe we can quickly draw the root locus and check. So I have a pole at -1, a pole at -2. So here the root locus starts, they meet at some point and then just go to 0. Like this is stable for all k. Okay, how does that show up in the Nyquist? So I look at this plot. So my point of interest -1 plus j0 is here. Open loop system is stable. So the closed loop system must have n equal to 0. So I start with a smaller value of k equal to 1. The system is away from my point -1 plus j0. The yellow line, k equal to 5. This is also away. The red line k equal to 10 is also away from the point -1 plus j0. So, so for all k greater than 0, n will be equal to 0, and therefore the closed loop system is stable for all k greater than 0. You can see this via the root locus. You can also see this via the plot here. Okay, let's go to the second plot. And of course, we have discussed this also a little in the past. So I have g of s is k over s plus 1, s plus 2. So just draw the plot here. So I have poles at the origin, a pole at -1, and a pole at -2. So what are the points on the root locus? If I just look at the real line, so this will be the points on the root locus. Then they will somehow meet here and then go away. So there will be some gain k, after which the system becomes unstable. So let us look at it from the root locus point of view. Maybe I'll just zoom in a little bit here. So where is my point of interest? -1 plus j0. That point is sitting here. Okay, so look at smaller values of gain k equal to 1, k equal to 1. I have that number of encirclements is 0, so the system is stable. Okay, then I go to, let's say I go to k equal to 10 here. K equal to 10, I have a plot. So this figure actually extends all the way like this. I just zoomed in around this point. So I have two encirclements. Okay, so I have two encirclements here, which means the system is unstable. This is for k equal to 10. For k equal to 5, I am at the point -1 plus j0. This is marginally stable when k equal to 5. Okay, I can also see that from my root locus, right, which I just draw. So this is the point where k equal to 5, system is marginally stable. Okay, so the system becomes unstable for all gain k greater than 5. Okay, there is another example which is the g of s is k s plus 2 s plus 1 s minus 1. Okay, if I just draw the full 0, so I have 0 at s equal to -2, a pole at s equal to 1, and the pole at s equal to -1. Okay, so for k equal to 0, the poles are at +-1 and unstable. So if I draw the root locus for this now, and we use a green pen. Okay, so this this part of the root locus will be okay. This part of the real line will be on the root locus. So this will come this side, and they meet at some point, possibly go here. So one pole will go to the 0 here, other pole will go to infinity. Okay, so the system starts unstable. Okay, the system starts unstable and then becomes stable after k equal to 1 by 2. We'll check why this we can quickly check. At this point, k will be equal to 1 by 2. So this should be k greater than 0.5. Okay, let me check the Nyquist. Okay, so at k equal to 1, k equal to 0.1. So I'm here. Where is my point? -1 plus j0 is here. So the n equal to p minus z. What is this p? P was the open loop unstable pole. So n must be equal to 1 for stability. Okay, check for what is for k equal to 0.1. K equal to 0.1, I'm really far away from the point -1 plus j0, n equal to 0, so unstable. Okay. So k equal to 0.5, I'm here, this becomes marginally stable. And for a value of k equal to 1, I encircle the point -1 plus j0 once, and then for this results in a nice stable configuration. Okay, so this is nice. This brings us to the notion of how relatively my system is stable. In one case, system was stable for all k. In other case, system was stable until k equal to 5. And in the third case, system was stable after a certain value of k. It started unstable, but actually became unstable. In the second case, it started stable, became unstable. Third case, it started unstable. Sorry, it started stable and remained stable for all gain k. Okay, so the first requirement in, of course, that the system must be stable. Next is to ensure that the system has adequate relative stability. Okay, so now how do I measure stability? So I do not want here that the system starts very close to the imaginary axis and slight change. So if I look at here, I say I start at k equal to 4.9, it will show stable, but a small change of k from 4.9 to 5.1 will make it unstable. Okay, so the first requirement is that the system be stable. And next is to ensure that it has adequate relative stability. And how does now one measure relative stability? Okay, so we look at how close we are to the imaginary axis. So this, if I'm closer, getting closer makes the system unstable, and then I go on, go. The makes my system less and less stable, more oscillatory. It has imaginary, marginally stable, and then goes to the unstable. So in my sigma j omega plane or the S plane, my cutoff point or my point of verification is the imaginary axis. Similarly here, it is the point -1 plus j0. So I can ask myself how far I am from -1 plus j0. So that will give me a little indication of how relatively my system is stable. So this Nyquist plot comes with an added advantage that it indicates not only whether the system is stable, but also the degree of stability of the system, and therefore also has information of how the stability can be improved. As I just said, so in the complex plane, I'm interested in keeping the poles to the left of plane. My gate was the j omega axis. In this case, the gate will be the point -1 plus j0. As the plot gets closer to -1 plus j0, the system is on the verge of instability. Like if you see in the second plot here, right? So this one, k equal to 1, I was fine. K equal to 5, I'm just at the border. So I'm just, and once I cross the border, I'm always unstable. Okay, so closer I am to the point -1 plus j0. Of course, you can also see when I'm closer to the imaginary, closer to the point -1 plus j0 would mean I am closer to the imaginary axis in the time domain. Closer to the imaginary axis, lesser is the zeta, larger is the overshoot. The limiting case zeta equal to 0 will have the largest overshoot, and anything closer to the will have a significantly large overshoot, and also a larger settling time. Okay, it's not just relative stability, but also I look at performance. Okay, so I am now interested in this point -1 plus j0 and a little circle around that. Okay, now how does one quantify relative stability? So if I keep on increasing the gain k, let me see what happens. So I'll maybe at some k, I'm here at a. Here I might be, okay, let me see the red one. Okay, so after some other gain, I might be here, some other gain, I might be here. Eventually, at some gain, I cross the point -1 plus j0, and then I go away. So this will become unstable. Okay, that's what we saw in the other plots also. Okay, so we can use now these quantities. So what are the two things here? I measure this number a and this angle phi, and we'll see how these two quantities can be used to define relative measures of stability or measures of relative stability. This will be known as the gain margin and the phase margin. The Nyquist plot crosses the So look at this. So I have two frequencies here. Okay, so I have two frequencies, omega 2 and omega 1. Okay, at omega 1, my magnitude of G of j omega is 1. This is at omega 2. And at omega 2, my imaginary part is 0, or it crosses the real axis, or the angle of G of j omega is plus or minus 180, depending on how you measure it. Okay, so the Nyquist crosses the imaginary axis as it should be the real axis. Okay, and then the unit circle intersects the locus at omega equal to omega 1. Okay, and the phasor of G, this is, so what is the phi? Phi is the phasor which I start from the origin. I look at this point omega 1. This will be my angle phi. Okay, so the phasor makes an angle of phi with the negative real axis as measured positively in the counterclockwise direction. That's the convention we have been using since beginning. As the point, or as the locus approaches minus 1 plus j 0, the relative stability reduces. And this happens when the value of A approaches unity and phi tends to 0. Therefore, we can, so A, so this is my A, right? When A is 1, this will become A equal to 1, right? Or when this phi, if I just go around along this this circle, I go around at this point, I will have that phi equal to 0. This is what these two things mean. As A approaches unity and phi tends to 0. And therefore, we can use A and phi as measures of relative stability. Okay, now I'll ask myself a question. What is the gain margin? It is a factor by which a gain can be increased to drive it to the verge of instability. I start with A, I increase the gain slightly more. So, yeah, I guess the gain like slightly more and slightly more. And what is a factor? There should be some factor A times some factor which will make it 1. This factor is 1 over A. If I increase the gain by a factor 1 over A, then I hit the point minus 1 plus j 0. After that, I'm always unstable. That is like the point, say k equal to 5 here. Okay, I start with a gain of 1. I go till increase it by a factor of 5, and I become unstable after that. Okay, so at omega equal to omega 2, the phase angle is minus 180 and the magnitude is A. If the gain is increased by a factor of A, then the overall gain now becomes 1, which means the plot will now pass through minus 1 plus j 0, driving the system to the verge of instability. Any further increase in gain will make the system unstable. So gain margin may be defined now as the reciprocal of the gain at the frequency at which the phase angle becomes 180. Okay, so nothing too complicated about that sentence. So we're just rewriting writing this down properly, right? So 1 over A. So this is A is the magnitude of G of j omega at this point omega 2 is A. This is called the phase cross over frequency at which the angle becomes 180. Okay, now just take so compute the angle, or so compute the frequency at which the angle becomes 180. That frequency is omega 2. Compute the magnitude at that point. Okay, that will be A. Do a 1 over A. This will be my gain margin. Okay, nice. So what else? Okay, the frequency. Okay, we just discussed this. The phase crossover frequency and all. Phase margin. It is the additional amount of phase lag needed to bring the system to the verge of instability. Again, the frequency at which the so we have. We'll go back here to this plot. I'll call this as the gain crossover frequency. This is the frequency at which the gain becomes 1. And once I know the frequency at which the gain becomes 1, so we'll have, so the frequency at which this becomes 1 is the gain crossover frequency. This is the frequency where the plot intersects a unit circle. At this frequency, what is the phase angle? The phase angle at this frequency is from here, if we measure counterclockwise, from here till here is 180 plus an additional phi. So the phase angle at this point becomes 180 plus phi. So if an additional phase is phase lag, right? So I have 180 plus phi. If I have a phase lag of minus phi, then so if an additional phase lag is introduced at the gain crossover frequency, the phase angle will become 180 minus 180. What is the gain here? What is the magnitude of Gj omega? This will still be 1 because I'm just moving along this direction here. I'm moving only along this direction. So the magnitude will remain unity if I just add a phase lag of minus phi. Okay, so that's what this statement means. Here, note that the magnitude remains unity. And once this additional phase is added, the plot will go through the point minus 1 plus J0. And this number phi will now be called as the phase margin of the system. So we have defined two quantities, the gain margin and the phase margin. So by definition now, the phase margin is defined as the additional phase lag at the gain crossover frequency to bring the system to the verge of instability. Okay, and the phase margin is always positive for stable feedback systems. Okay, this is the general formula for that, but pictorially that's what is happening. Okay, so I'm interested now in three quantities. I'm interested now, I call this as the gain crossover frequency. I call this as the phase crossover frequency. I measure how far I am from the point minus 1 plus J0 via the magnitude and also via the phase. Okay, so this is a summary of what we have done. So some things quickly to verify. If the phase crossover frequency is greater than the gain crossover frequency, these two things will always be true. The system will be stable. If both are the same, the gain crossover and the phase crossover are the same, the system will become marginally stable. And if the phase crossover frequency is less than the gain crossover frequency, the system will become unstable. Think about why these conditions are valid. It's a very simple computation. If not, we'll discuss in the live, one of the live sessions. Thanks for listening. Next time we will start our discussion with another frequency domain technique called the Bode plot.